Tергול תגיד so?
כן.
כן.
אתה רוצה מים? מה קרה?
מה? קורה?
מה?
סרט.
כן.
Those filthy liars. אני יודע שאנחנו בשיעור. Okay, hello everyone, all of you guys. Yes, so today we're going to talk about photo detection theory, and then we quantize the field. And since there's so many people here, we'll go until everyone's tired.
Classical coherence?
Yes, it's in the classical coherence total page. Right. So in the lecture, you saw that semi-classical theory predicts that the photon count would be perfectly constant to basically, to make long story short, we saw in the tutorial that for a semi-classical field, the clicks in photodetectors, which will be calling down for now photon count, will have this distribution, depend on n and t. Equal t, right? Well, lambda here is the rate of the Poisson process, and it's also depending on the response of the detector. This distribution will have the variance. You should also have seen this in the tutorial, in the lecture. Minus average n squared should be equal to average of n, and the signal to noise ratio equal to n square root of n delta n squared is equal to square root of n. This is the signal to noise ratio, which is in this case the perfect detector with the short noise limit. And later on you will see in class that this is the actual short noise limit, not related to the detectors. Just a fundamental concept. Right. Let's try for an example to calculate the second order, just to understand some statistic, so we calculate the second order of n. I mean this one. So we'll go over a little bit back on statistic and specifically what happened here. Well, first of all, to calculate this expectation value, what we do is we take a sum of all the possibility and multiply them by the thing that we want to measure, then multiply by the probability of the thing that we want to measure. Right? I will also arbitrarily here. It's a bad marker. Add and reduce an n, so n squared plus n minus n. N should be equal to sum over n and n minus 1 p of n plus sum over n p of n, right? This right here is the average number of photons, okay? This part would be, if we open it up, sum over n minus 1 over n or e minus expectation value of n equal to expectation value of n squared. I'm going to take 2 to the outside and reduce the denominator these two, sum over n and n minus 2 power e minus n is equal to, I can now exchange the variable n to n tag, so I'll remove the minus 2, it will be squared, so tag n tag divided by n tag power e minus n, which of course this is just p, sum of all p, so this is 1. Overall, you get n squared equal n squared plus. And from this result, we can quickly see why the variance is just the expectation value of n, because this will be equal to this one, which is the same thing. Okay, now if we call this sort of distribution which hold this parameter Gaussian distribution, but we can also have the case with the field intensity fluctuate, and the statistic will be called pseudo-Gaussianic, in which case P and T will be equal integral over I, Pi, nu I T power E minus nu I T. Yes, where note that this part is basically, should have made more notes on my note. Right. In this case, we'll see an interesting discovery where the average of expectation value that we want, delta, will be equal to something is wrong.
זה קשור להגדרה ששלמנו בהתחלה.
Yes. Yes. Okay. Yeah, I should have put more. I actually wrote on this tutorial because I don't like how it's written. Anyway, yes. In this case, actually, the fluctuation in I is fluctuation in the delta here. So the average of the delta in this case, which is a super Gaussian case, because you also have the field fluctuation in N and T for measurement, and the fluctuation on the field itself is called super fluctuation, where the variance is larger than the expectation value. In this case, the expectation value of the fluctuation will be nu I. That's how we define them. basically, this is very easy to see. Basically, the delta here, which dictates our photon rate, will be replaced with the intensity of a field times some constant. And in this case, where both of them fluctuate, we can look. I don't think we won't do it here. I'm pretty sure. You can see that the variance also will be squared plus squared. This will be super-Poissonian statistics. It's not very important to remember or know why right now. But there's also sub-Poissonian statistics, which we can't do now because it's very much not classical. Again, sub-Poissonian statistics, just like super-Poissonian statistics, we just statistics when the variance will be lower than our expectation value. And you'll see it when we go into quantum mechanics. Right? Okay. Hmm? Right. What? Okay. I know what's going on. Right. Let's do a little example with the Poissonian statistics, and yeah, that will be it for now. Let me see if there's anything here very important, because I really want to go into quantization of the field. Let's just, okay. We know we have a system where we know that the expectation value of n equal to 50. We want to find P48 between 48 and 52. Well, we know that P of n would be equal to 50 to the power of n divided by n. How? P minus 50, right? So if you want to find P between 48 and 52, we equal to P48 plus P59, so on and so forth. You can see all the numbers in your notebook. Overall will be 0.27. Very interesting. Now the second part of the question.
Why are you adding instead of multiplying?
If we say that we want to be between 48 and 52, then that means I don't care if we have 48 photon in a result, or 49, 50, so on. So we want to what's the probability we get 48? What's the probability we get 49?
And then
So both of them together. So the overall option to get these numbers, right? Okay. Now we're asked a question. We want to take this Poisson this distribution, which is quantized discrete distribution, and transform it to Gaussian distribution, because we always talk about everything in quantum, everything in statistics, non-Gaussian and stuff. So if the Gaussian distribution in general looks like so. E minus n minus square divided by square. And since we know that our variance will be n, I can also replace sigma squared with the expectation value of n, because this is just the variance of a Gaussian function. But the Gaussian function is not discrete, it's continuous. So instead of the summation, we're also going to take integration. Okay? So P 48, 2 would be the same as taking P n smaller or equal to 52 minus P n smaller or equal to 48. This transition, you understand this transition? Right? It will just be integration tends infinity to 52 1 over 2 pi n square root e minus n minus squared divided by n minus integration from minus infinity to 48. The same thing, but you can put it in a calculator, so complicate, it'll be 0.223. So it came out way wrong. What happened? What did we do wrong? Any of you have any guess why did it not agree? It didn't do anything crazy. This is a general Gaussian distribution. Gaussian distribution is definitely the continuous variation of the Gaussian distribution. It's just the Gaussian is discrete. Gaussian is continuous and both the same.
Gaussian for a specific number is 0.
Yes, but that's why we integrate. Gaussian, you can think of Gaussian as like the probability distribution that describe the Pearsonian distribution. Right? The yes.
But you take in the upper side, you take a discrete sum of the Pearsonian, and in the Gaussian, you take the continuous sum.
All right. So what's the problem?
Gaussian for a specific number is 0. No?
Yeah, but it's not a problem since I integrate. I don't take a specific number.
It doesn't count for 48 and 52.
Let me ask you a question. Yes, that's also very good. Actually, we do count 52, but it's almost there. Let me ask you a question. Let's say I try to measure some continuous process, and I get 51.7.
51.
Is it 51? Is it 52?
It's not exist in the Pearsonian.
Right. It doesn't exist in the Pearsonian, that's correct. But the point is that we don't, let's draw it, and we have the Gaussian, and we say, let's say this is 52, and this is 48, let's say this is our numbers. Taking the integral between those, right? Exclude values over here, and we need to think about it that every point in the Pearsonian distribution will not be a specific point of the Gaussian. It will be an area around them. So what we need to do is actually take another half step in each direction. So instead of 52, it's going to be 52.5. And instead of 48, it will be 47.5.
Why half point?
Second. Very good. It will be half point because this would be the area where we can definitely define as all the answers over the concluding into 52. 52.1 is 52, not 53. Okay. We basically take an area size 1, an area the size of the point around each of our point. Right? And if we do this change, we'll see that we do get 2.76.
So always half.
Always half in this case, yes.
So take the upper limit, right?
Hmm?
We take the upper limit for each one of them.
We need to basically. I'm only doing it in 2 points, but think that I'm trying to segment my Gaussian space into all the points. There's point 1, which has a section for 8.0, which has a section point 2, point 3, point 4, and I need to cut the Gaussian space into this point. So we don't go all the way to 52. We take the entire area that define the measurement 52.
Okay.
You want to go quickly?
Yes.
Yes.
Well, the second example in this formula decline is again just about statistics. So I think we can just go into quantization of the field right now. Also, I don't even remember if you have homework about photo detection.
וזה אני חושב שאתה צריך לעבוד אותה.
לא נראה לי תיקנת את העלאה של
של התרגול לפני שעבר, לא?
של השיעור.
זה עכשיו עושים.
מה?
עכשיו זה בדיוק מה שעושים עכשיו.
לא, הקביטות זה תרגול הבא. Move to the next tutorial. Are you okay? Did you find it? I'm also take where is it? Go to the next tutorial, quantum state of light. Right. In the lecture, you saw that an electric field can be displayed using the Hamiltonian K equals h bar.
Sir, are you sure that you upload this tutorial 7?
Never use it.
אז די, אני חושב שפיצים מהרגע שהוא יצא, אתה בטוח, נכון? לא. יש פה...
Okay, now it's uploaded. Forgot to reveal it.
Okay, thank you.
All right. Before we go into it, let's talk about basically. You saw that we can define every electric field as a ladder system where we add quantas of energy. So that in class, which is operator called the ladder operator, or the annihilation or creation operator, where we basically create a phonon, or in this case, the phonon is a photon, or annihilate a photon, which is like a phonon. And we know some special characteristics that these two operators have. For example, they have a commutational relation between them. First of all, AK tag equal to AK dagger into 0, and AK tag dagger be equal to delta K tag. This is the fundamental of how we write and calculate and transform function in the quantum mechanics. When the commutation relation is equal to 0, that means that we can freely replace the order, change the order of operators. But if it doesn't equal to 0, it means that we can't freely change the order. Just to remind everyone, this commutation relation will be equal to AK tag dagger minus AK tag dagger K, right? So you see, if I want to transform AK dagger to AK dagger AK, I need to add a little extra there. Additionally, I will just mention it because it's important, but it's not in a course. There's also anti-commutation relation, which has a plus here, and we usually write them with curly brackets. I think they're called curly brackets, I don't know. And those, if you're interested in what they mean, normal commutation relation apply on bosons, which are photons, protons, all sort of stuff. And anti-commutation relation usually apply on fermions, like electrons, stuff like that. They both have somewhat different fundamental mechanics within them. But you'll see it if you take some advanced quantum course. You get closer into it. All right. The first easy states that now after we formulated the quantum field, quantum operators, the operators are analogous to field in classical space, and the Hamiltonian, of course, is analogous to energy in the classical form of writing. And now after we define those, we need to talk about actual states, which is the thing that live in our system and whatnot. And the first easiest state to talk about is the number state, or as we call it, the Fock state. So let me just write them.
The
Fock state. That's how it's called.
Okay,
F-O-C-K. A. Let me just rewrite the Hamiltonian, and you will see in a second why. Well, n is equal to A target A, right? And I want to claim that n is the number operator. So I'm not going to prove it here in this tutorial. Did you prove it in class that n is the number operator?
1 to 1.
1 to 1? Okay, so without any proof, let me just give us some steps that will help you understand why is it the case. A few rules. The creation operator on a number state. Note that a number state is basically saying how far we are on the ladder. We are n step over 0 on the ladder. This would take us up one state and add a normalization factor of n plus 1. And the annihilation operator would reduce us one state and give us a normalization factor of square root of n, not n plus 1. So if we take A dagger A, n, we get square root of n, A dagger n minus 1, then n, n. So this will be equal to, okay? So the Hamiltonian, the energy is the effect of the Hamiltonian on the number state would be h bar omega n plus 1/2. Okay. Right? And since the state didn't change after the Hamiltonian, we call it an eigenstate. Like eigenvector, eigenstate, eigenvalue. Great. Alright. Now it's also very nice to talk about the commutation relation of n. Do they ever have a good marker? Let's see if the red works. Okay. And dagger, and A for minus A. Technically, I should have also indexed all of this operator and add a delta, but it's fine. You'll get it. And
like NK, AK.
yeah, NK, AJ was, and then here will be a delta KJ.
So for
Do
each
you
K
need me to
mode,
prove this?
No.
so for each K mode we have different energy level.
For each, yes. Okay. So in quantum mechanics, two phonons generally, unless there's a medium, will not interact, and there will be in a completely separate states, which can be defined by K, the energy level, but it can also be defined by a lot of different parameters, like polarization or stuff like that. So we indicate them with indexes or some other form of writing. So note that when I say ladder and I climb up the ladder, it doesn't mean that I add energy to the photon. Is that here it technically means that I add more photon to the same energy level. So there are 1 photon, 2 photon, 3 photon, whatever. It's not the same as increasing the energy of the photon. Really different. Okay. So one second. Okay, I guess I will prove this. Right. So how did I get here? Let's just do it in the annihilation operator. Let's say I'll take this equation, and instead of writing it like so, I will add an n for it, and I want the n to operate on this weird state of a n, right? This will be equal to a n, right? I reverse the order, and I take, and because I reverse the order, I have to take the commutation relation, and the commutation relation. So it's minus a times n, right? Now, if we take a to the outside, we see that we are left with n dagger plus a minus. Note that I don't write 1, although 1 would also be fine, because I want to cement into you that all of this is approximately of matrices. And yeah, so overall we'll get n minus 1 a n, right? Because I is obviously n is obviously an eigenstate of I with the eigenvalue of 1, and it's an eigenstate of n with the eigenvalue of n, since we define n as the number operator, right? But note that n minus 1 is the eigenvalue of n if this term will be equal to n minus 1, right? But we need to also have a normalization. We also need to add a normalization, which will give us the square root of n here. Okay. Overall, we can do the same exact process to prove this point, so that you believe me by now. Now, these processes, this operator, we can also do them in reverse. Basically taking n plus 1, square root of n plus 1, and then taking an a dagger outside. I can do it again and again and again and again. And overall, we'll get, I'll put it here, that every state n will be equal a dagger n divided by square root of n. Or, right. Now we'll talk about the next important part of quantum optics, quadratures. Crazy. Quadratures are quality of fields that you can even see in classical mechanics. Usually we talk about position and momentum. And in quantum mechanics have the canonical commutation relation of I each bar. But in quantum mechanics, you don't physically describe the position and momentum. They describe the in-phase, in-quadrature, as we call components of the operator, where A equals the square root of m omega 2h bar x plus I p divided by omega. They tell us a lot about the statistics and the distribution of our field of operators, but we won't really go deep into this. We'll go into this in a second in the tutorial. And it's usually comfortable to define also the normalized quadratures, which is x divided by 2h bar divided by omega square root and p. With this one will be better. Oh. B divided by square root of 2 h bar omega, which will simply give us A equal 1 over square root of 2 x plus I p. And this normalization will also be very nice in the commutation relation. We just turn it into I. Right? You can also think of it as a bifraction of the field to any two orthogonal components. For example, the real part of a field and the imaginary part of the field, and so on and so forth. From here on out, I'm going to write x and p not in capital letter because I don't want to write all this line every time. You just know that I'm using the normalized equation, normalized part. Another example that we can equate quadratures to will be a phase and intensity. You can measure the phase of a field, the phase component of a field, or the intensity component of a field. I can throw in another, I can throw a lot of other examples, but I think you get the point. Additionally, quadrature, if you pick a quadrature right, that the other two are trigonal, meaning that they do not commute between each other, not equal to 0. You will also meet, I don't think we prove it in this course, and I'm not going to do it, but we also meet the uncertainty principle. If someone wants for me to prove it, we can do it later, doesn't really matter. And another interesting quantity is that the position momentum space in this position momentum quadrature will have a 0 expectation value in the number space. And soon we'll also see how they look like. Also interesting that because they have zero expectation value, we can look at the expectation value of the field, of a classical field, of a classical quantized field. We know that the classical field will be equal to pi h bar omega divided by v x cos omega t minus kr plus p sine omega I. Hey? Which was the 9? Omega k minus omega t minus kr. And you will see that if we do an expectation value over it, all the numbers go outside, and the expectation value will follow the operator itself. And since the expectation value of x and p will be 0, this will also be 0. And we indeed cannot directly measure the classical field. There's no specific law. Right? Okay, now let's move to the first interesting state, which is the coherent state. The number state is very cool, it's very nice, very useful, but it's not real. You will not find any system in the world that has Fock state n equal to 128. You can't do it. It's not feasible. I think the biggest one that I heard of is a system that uses n equal 2 or n equal 3. Usually, most state that we see, for example, what comes out of a laser, is a coherent state. We'll talk about now, right? Yeah, those fundamental fields in quantum objects, which are lasers, and they are defined as the eigenvalue or eigenstate of the annihilation operator. So what I mean by that, find A alpha equal to alpha eigenvalue. Note that alpha does not equal to alpha. These two are not just the opposite of one another, right? But we can say alpha acting on a dagger would be equal to alpha conjugate. Right? You learn a little bit how to work with operator in states, understand why this one is equal to the conjugate of this one. Okay. So, yes, if you take a classical field and classical field operator and try to do the expectation value this time on alpha and not on n, we'll see that we have constant pi h bar omega divided by v times alpha is the minus I k t minus k r plus alpha divided alpha e to the I omega kt minus kr. This will give us alpha. This will give us alpha conjugate. And overall, this will be equal to square root of pi h bar omega v real alpha e to the minus I omega k t minus k. Which this is much closer to what you'd get if you would be able to measure the classical field. You will only get a cross section of it. In the real state, you will need some real numbers, some real result in the end. To do this kind of expectation. expectation value. Which is much closer to the classical state. The Fock state is very quantum and will be precisely 0. Right? Now we'll go a little bit over about the statistics. now להפריע בשיעור. אוי, לא.
Oh no.
Oh no. מה השעה?
עכשיו 6:50.
כן, זה מוקדם אפילו.
אין, יש עוד 9 עמודים.
9 עמודים? וואו. אוקיי. Okay. Now we want to practice a little bit of the coherent state. So let's do an example. Wow, yeah, we do have a lot, so we might skip a little bit. But let's start the example and see what's going on. We want to, first of all, example, we start with the coherent state. We want to find alpha. Okay. So alpha can be equal. Alpha is defined on the annihilation and on the annihilation operator, so I'm going to transform x to annihilation equation. Be equal to 1 over square root of 2 alpha plus alpha dagger alpha equals square root of 2 alpha. Similarly, p alpha will be equal square root of 2 imaginary alpha. Which again kind of makes sense if alpha is supposed to be analogous to the most classical field, and x and p would be analogous to the real and imaginary part of the field, imaginary and real part of the field. Right? Now, classical field have no uncertainty, but quantum field do have uncertainty. Let's show that coherent state is a minimum uncertainty state, which means that the uncertainty in x times the uncertainty in p is equal to 1/2. It's the minimum of the uncertainty principle. Right? So for that we need a marker that works. Yes, but I have more. I have so many more. All of them in one. So alpha square alpha so be equal to 1/2 alpha a plus a dagger squared alpha, right? But 1/2 alpha a squared a dagger a plus a dagger a plus a dagger squared. Again, note I didn't combine them two because they're commutative. Right. This one will be alpha squared this direction. This one is a bit of a problem, we'll talk about it in a second. This one, alpha dagger, I can operate it to the left, alpha I can operate to the right, be absolute value alpha. You're right. We have alpha squared plus absolute value alpha squared. This one will be plus alpha conjugate squared. Now this term, a dagger, we know that it equals to a dagger a plus 1. So we have plus, again for some reason here, plus 1. And overall delta square would be this minus well, which we did here. So we have equal to 1 over 2 alpha squared plus alpha conjugate squared plus 2, so the value alpha squared plus 1 minus 1 over half alpha plus alpha conjugate squared equals to 1 half. X equal to. You can trust me, you can do the math yourself. Comes out to 1 half, and delta x will be equal to 1 over square root of 2. And I believe it's not very unfeasible that delta p would be the same. And overall, we see that the x times delta p equal to 1 over 2, which is minimum uncertainty. But we see something a little crazier here, in my opinion. Crazy. That the uncertainty.
Shouldn't it be 1 over square root of 2?
What?
Shouldn't it be 1 over square root of 2 the uncertainty principle? Like
No, 1 over 2. Half. Well, you're gonna fact check me. I'm welcoming it. It's good.
No. לא, חצי.
הייתי כבר כאילו שווה לך זה.
כן.
Okay. So, okay. But we see that it's also, I think it's very cool, is this! Dun dun dun! Can you venture a guess why it's so cool?
What is the magic?
Right? What happens if I have a coherent state with an intensity, with an amplitude alpha of 1? What's the uncertainty? What if I have an amplitude of 1000? What's the uncertainty? 1 over the square root of 2. 1 over the square root of 2. No matter what. So that means if I want to write, I'm also going to skip the next part of the question because I don't want to do the math, but you believe me, if I take some quadratruths in between, for example, cosinus theta x plus sinus theta c, write something in between, the uncertainty, you will trust me, will also be 1 over square root of 2. That means that if I make a diagram in a space that is span over x and p, so p x, no matter what the alpha would be, always going to be a circle, a Gaussian with the width of 1 over square root of 2, or 1 half, because we can take square, whatever, you get it. This would be here, 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 here. Right? Here, 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 here. Okay, let's see the next part. I didn't get a chance to go over the tutorial for the class. Let's see the next part is interesting. Alright, yeah, let's do it. So the next part, C, is we want to find the mean and variance in number of photons in the coherent state, and by that we can show that it reproduces the classical photon detection statistics that we discussed previously. All right, so remember this diagram that I wrote because it will be important in a second. All right, this one equals to alpha a delta a alpha, which of course is absolute value alpha squared before, and alpha n squared alpha would be equal to alpha a dagger a alpha would be equal to, I'm gonna put it on both, So we got alpha, A dagger, A plus A dagger A, alpha equal to the value alpha to the power of 4 plus to the value alpha to the power of 2. Therefore, delta n squared will be equal alpha to the power of 4 plus alpha to the value of power 2 minus alpha power of 4 alpha power of 2, right? Which will be equal to expectation value of n. Now, I believe that I don't have to prove it to you. This is just a Gaussian distribution. Gaussian distribution and Gaussian distribution is the same because the variance is equal to the expectation. Okay? So now let's try to see what this state actually is. What is this state? Can we represent it in the ladder, the Fock state basis? Let's start by assuming that we can do it. Okay. Right? So let's start by assuming that we can do it. It's equal to over n, Cn, then some constant. Right? We assume that we can do it. Right? And we know that if you multiply alpha by the operator A on alpha, we would get for one side Cn square root of n minus 1, but we also know that it will be equal to alpha, right? So Cn plus 1 will be equal to alpha square root of n plus 1 Cn. Right? This connection comes from here by just moving the n1. Right? So we know that Cn must be equal to alpha to the power of n divided by square root of n power C0. Okay. And now we can find C0 by taking the expectation value of alpha on nothing, multiplied with itself. Since it's a real state, a normal state, it should be auto-normal to everything else. So the auto doesn't matter, but the normal is what's important, meaning that the multiplication must be equal to 1. Multiplication of him with itself. So multiplying him with itself and putting this addition in, you have C0 absolute value squared times sum over n equals 0 to infinity alpha power of 2n divided by n power without square root n power. This sum is just a Gaussian, so it's C0 squared e to the absolute value of alpha squared equals 1. C0 equal to alpha to exponent of alpha of minus absolute value alpha squared divided by 2. I think there's missing a minus divided by 2 in your notes.
Yeah, there is.
Oh, okay. So overall alpha will equal some n equals 0 infinity alpha n divided by square root of n power e to the minus alpha to the square divided by 2 and Pn would be equal to n alpha to the value squared just be equal to alpha to the power 2n divided by n power e to the minus squared. This is a Gaussian distribution. Alright. want to talk to you about a very special case. We didn't talk about it yet, but in quantum mechanics, vacuum is not nothing. Vacuum is also a state that we need to that has a distribution of 0 photons. 0 photons, 0 amplitude. It does have a variance in some characteristics, but it's just the state defined as 0. Note that when I'm saying state defined as 0, I mean this thing, not this thing. Because this thing also exists in quantum mechanics, 0, but it just means nothing. This means vacuum. It's two different things. Right? Now,
you do the displacement operator?
what?
You do the displacement?
I don't understand what you're asking.
You do
In
this.
the tutorial, are you in the displacement operator or
No,
that?
before that, just before that. But we'll jump to the displacement operator in a second. It's just going to be that tutorial. Now, yeah, I'm not going to go over what the tutorial said about the vacuum. I'm just going to talk about it a little bit.
Because Abi didn't do the displacement yet.
So, I don't know if he was so busy that I didn't have time to check with him how far I can go. But I think we will just do the displacement operator and that's it. Maybe, I don't know, we'll see. Anyway, the vacuum state is a very interesting case because n of the vacuum state 0 times 0 to 0. So the vacuum state is an eigenstate of the number operator, which means it's a Fock state, but A0 equals 0 times, I'm going to write something blasphemous. It's 1, 0. There is no minus 1. There's no really minus 1. Oh, don't kill me. Alright? So it's also an eigenstate of the annihilation operator, again with an eigenvalue of 0. So the 0 state is both a Fock state and a coherent state. Pretty cool. Now, how do we create? Let's do the displacement operator. Let's do it, and then do we do squeezing here? I don't think we do squeezing in this tutorial, so we're not going to do squeezing. I don't know if we're going to do phase states.
Nah.
But note that in the website there's 2 different notebook explaining a little bit about phase state and why phase is such a problematic thing in quantum mechanics, even though most people ignore the problem that it brings up. If you want to, it's not part of the material of the class, but if you want, you can go over it. It's pretty interesting. All right, so we want to start with a vacuum state, 0, and then use some operator, let's call it D, alpha, to generate the coherent state. How do we do it? Well, luckily for us, it's a very well-known transformation. In the X and the P, it's written as P X minus X P. Right? Note that P and X are value, and X hat and P hat are operators.
What is the meaning of that?
It's the value of the field that you want to get. Like, where do you want to put it in the XP space? If you take, for example, the X and P to be the real imaginary part of the field, that means that you want a coherent state where the average real part is X and average imaginary part is P.
Okay.
Right? Locally. And we can also define it in a much more sane space, sane writing, which is in the annihilation and integration operator. A9 minus conjugate A. Now here comes the question. Oh no, there's no question. We do actually prove it. So let's try to prove that this one is a displacement operator. Right? So we want to use this operator on the vacuum, get to the end. For that we need to yeah, I'm sorry. We need to use the Baker-Campbell-Hasdorf formulas.
So
Yeah.
what is the difference between an operator and just like between the P and the P operator? Like what is the meaning of both of them?
Right.
The essential meaning of
An operator is, you can think about it as a matrix, is some catalyst of transformation, of interaction, of, you know, this is how we move in the state field. I don't know. That's how we move through states. That's how we transform operators. It's the basis of quantum mechanics, and this P and this X are just numbers. Or values. I mean, they're values with meaning, but again, they're just values.
so like the X is the spatial coordinate and the X hat, it's the coordinate of the vectors transformations.
No, think about it as a. Again, it's the best to compare it to matrices. I can write 6 times 1 1 0 1, right? Okay. Let's do actually something a bit cooler. Now it's 6, right?
Okay.
So numbers in quantum mechanics are essentially, they could have meaning. For example, here it has a meaning to it, but they're essentially just numbers, just like you know in normal life. And operators, sometimes you write them with hat, sometimes you don't. It's okay. And operators, they are the, you can think about it as the engine of quantum mechanics. They are what actually transform all of the function and the states and whatnot. They
are transformation between states.
yes, they are like a function that says there's going to be transformation here. There's a lot of, and again over here also, like number have context to them, also operators have context to them. For example, I erased the Hamiltonian, but for example, when you have a dagger A in the Hamiltonian or something, we can think about it as, okay, this is just, it counts the numbers. Or we can think, all right, it scans the field, it removes a photon, and by that taking the measurement, then putting it back in. There's a lot of way to look at it, but essentially, operators are just the, yeah, I think the engine is a good metaphor. Yeah, but the other building block, honestly, I would recommend just sticking to the math quantum. I think it's much easier to digest like that, and then each case on its own, you can try to figure out what it means. And I don't know if you take like advanced quantum mechanics courses in your studies, maybe this degree or another one, but you will see it very much more in detail over that. Also, directly, how do we get into the ladder operators, the meaning of phonons and stuff like that. Also, a course that I teach, so I like it. Where was I? I don't remember.
Yeah,
Oh yes, I'm starting with Baker-Campbell-Hasdorf. Of course. Who didn't hear of this? Right. So, yeah. Okay. So, Baker-Campbell-Hasdorf, two different equations. If we have two operators A and B in an exponent, they will be equal to the exponent of A plus B plus 1/2 the commutator A and B, right? Plus 1 divided by 12 the commutator A and the commutator of A and B, right? Minus 1 over 12 the commutator of B, A and B, plus whatever, so on and so forth. And another one, if you want to, okay, this is a canonical transformation. See it? Because a to the power of e to the power of minus a times e to the power of a equal to 1, this means that this is a canonical transformation. Because this is a unitary matrix, essentially unitary matrix and unitary matrix. This will be sum over n, a, b, whatever n power, right? 8, maybe. This is n, like so, where a, b, n would be equal to commutator A, commutator A, commutator, until you have commutator A, B, where the number this happen n times, right? So we'll use the first relation. We'll use the first relation to prove this one, and we'll use the second relation to show how we can do the same thing by changing the annihilation operator. Because I don't know if Avi talked to you about this, but there are two main ways, a little bit more than that, but there are two main ways to work in second quantization, which is what we're doing here. We can either evolve the states in time, or we can evolve the operators in time. Both of them are equivalent if you're consistent. So with this, we're going to show the evolution of the state, and with this, we're going to show the evolution of the operator. So erase here. I really need to start segmenting my board. I am all over the place.
Yep.
Okay, so let's start with the state. Okay. We have first, if the commutator, this commutator is 0, then all the rest in the line will also be 0, and we will only be left with these 3 terms. This will happen if this commutator is just a number. Okay, so commutator between A dagger A, of course we know it's 1, so the commutator between A dagger A and also the value alpha, because we have alpha conjugate here, and we can take number outside of the commutation relation, would just be, oh sorry, this is minus, outside minus here, so it will just be absolute value of the square, right? So E, the alpha, E dagger minus alpha conjugate A, using the reverse of this relation, would be equal to E to the minus 1 over half absolute value alpha squared times E alpha E dagger E minus alpha A 0. Now there's a very important context here. An exponent on an exponent of an operator on an eigenstate of the operator will just allow us to replace this with the eigenvalue. It's a special case for exponent. So instead of having an alpha over here, we can just put zeros. So this the entire thing just be equal to the state 0. And now this exponent, we can develop it into a Taylor sum. This is completely legal and operator. So we'll have e to the minus 1/2 of the value alpha squared times sum over n equals 0 to infinity, alpha power n, a dagger n divided by n 0. And this is, I don't know if I erased it or not, but this is what we saw before to be the state, the current state. All right. Now to transform the operator A, if we want to go to what's called the Heisenberg picture, this is the Schrödinger picture. The Heisenberg picture, we take, oh no, you think I'm done, huh? You think I don't have any more markers? Suckers! You think this is my first rodeo?
מתי שאתה צריך לחשוב אם זה הסימן שלך מאלוהים להפסיק את התרגול.
Never! I would never stop. We have to take this. So we have E alpha conjugate A minus alpha A dagger A E alpha dagger minus alpha conjugate A, which will be equal using this sum for n. Yeah, I'm just going to finish this and then we're going to finish the tutorial. I'm also A and divided by n power. Okay. Now note that the first order, alpha A dagger minus alpha conjugate A conjugation of the A, this one, right? 0 means there is nothing. Remember, we count the number of times, so it's just going to be B, which is A, yeah, right? Oh no, A, okay, and 1. So I'm just going to do 1 would be, right? A with A, we can separate contraction. Contraction is the other word for it. I use a different word for it. Commutation. Relation. Yes, we can separate them. No, there's a word for it and I forgot it. It doesn't matter. A with A is 0. A dagger with A, it's 1. So it's just equal to the 1 times alpha, so it's just alpha. And you'll believe me that the same 1, 2 will be equal to 0, because we'll have alpha commutating with A, 0. So overall, all of this is equal to A plus alpha. So this is actually a moment of revelation, I believe.
Why alpha not 2 alpha?
Because this is alpha.
Ah, okay. I thought this is 2 alpha.
Oh, this is an equal sign.
Kind of.
Don't judge me. I'm tired. Anyways, this is a moment of revelation. You remember when I said that a vacuum is a special case that is both a Fock state and a coherent state? Well, it's not only that it's both a Fock state and a coherent state. It's both a Fock state and every coherent state, up to a constant. Basically, every coherent state, every laser which is a perfect laser, every perfect laser, you just take in the vacuum and moving it to alpha. This is lasers. I just take the state and move it a little bit. Take the operator and move it a little bit. Okay, so let me see if there's any other question on coherent state, something, I don't know. Coherent states are very cool, very useful. That's about it. Okay. let's go home.
זהו, הביתה ואז תפיל. יאללה בוא. צריכים לעשות עוד ערב אוכל.
כן, נדבר על זה.
שיהיה מוקלט. מי כבר יראה? דפנה? עומר? עומר גב? דפנה שמעוני?
אני חושב שהמזכירות שעורכת את זה, כאילו חותך להם לסוף את זה לך.
לא, צריך שדפנה שמעוני, עומר גב. מי אנחנו רוצים הקדשה?
אליי.
ואליי יראו את זה. תודה רבה, להתראות.